Welcome. On this video, we're going to be discussing the fundamental theorem of algebra and linear factorization theorem using complex and real solutions. So let's get started. Now, let's start by defining the fundamental theorem of algebra whenever we do have complex numbers involved. So the fundamental theorem of algebra, it will state f of x is any polynomial of degree n where the degree is greater than 0. Then we can say that f of x has at least one zero or one solution in the complex number system. So what do we mean by this? Well, this means that for any function, there's always going to be one complex number as a solution. Now we gotta be careful with that because complex numbers, and let's give some examples, because complex numbers can take the form of the real plus an imaginary. So here we have two complex numbers. That's one complex number and second complex numbers. And also any real number, I don't know, I'm just going to choose 10. Any real number, it's also considered a complex number. Why? Because 10 can be written as 10 plus 0i. So this is just a little bit confusing when we first stated, but when you see that any real number can be rewritten as a complex number, then this statement makes sense. It says, look, for any polynomial that you have, there's always going to be one complex number as a solution. Sometimes that complex number can have a value as an imaginary part, and sometimes that complex number can just have a 0 on its imaginary part. So that's the fundamental theorem of algebra, looking at it from the perspective of complex numbers. Now, what is the linear factorization theorem stating? Well, it states if f of x is a polynomial of degree n, so if you have any polynomial of a certain degree, then that function f of x has precisely n linear factors. In other words, we can just rewrite any polynomial as a coefficient where we have x minus ci, where those ci's are just going to be complex numbers, times x minus c2 times x minus c3 until we have x minus cn. What this is saying is, let's assume, and let's give an example. Let's assume that we have a function x to the fourth plus 3x to the third plus 2x to the second plus x plus 20. What this is saying is that I can rewrite this function as some coefficient times x minus 4 times, because I know that this must have 4 solutions. So therefore, I can just rewrite it as 4 types of linear factors. So if my highest exponent would be 5, then I could rewrite this function using 5 linear factors. And by linear factors, we mean binomials of the form x minus some number. It's a linear factor. So if we put it all together, we're saying that any polynomial has at least one complex number, and we know that that polynomial can be broken down into n linear factors, where n is the degree of the polynomial. The last thing that we want to state before we actually go to do some examples is the idea of complex numbers as solutions. And this is something that's going to be very important for you to understand, and that is that complex numbers as solutions they always come in pairs. So what we're trying to say here is that there's no such a thing as just saying, well, there's only one complex number as a solution for this polynomial. No, they always come in pair. So you either have 2 complex numbers as a solution, or 4 complex numbers, or 6 or 8 or 9, they always come in pairs. You do not have just one complex number as a solution or three, they need to be in pairs. Now, what is this second solution? Well, the complex conjugate of a complex number is always a solution. And we're going to take a look at some examples where we're going to be using these three ideas. The idea of fundamental theorem using complex numbers, linear factorization theorem as complex number, and the idea that complex numbers, they always come in pairs. So let's keep these three ideas in mind as we're going to the following examples. Because now, what we want to say here is the following. It says, write this polynomial as a product of linear factors and list all the zeros. So now, let's see, what do we know about linear factors? Well, the first thing that we notice is the following. I can see that my highest exponent is 5. So therefore, I'm going to be able to just rewrite this function as just 5 different kinds of linear factors. So we got 1, so we got 2, so we got 3, so we got 4, so we got 5. I know that my highest exponent is 5, so therefore I can just rewrite this function as 5 linear factors. 1, 2, 3, 4, 5. Now, how do we obtain those values? That's where we're going to be using some techniques that we have discussed before. Now, on the right-hand side, this is the function, or this is the graph interpretation of the function that we do have under example 5. And the first thing that we notice is that we can get some solutions from this function. Notice that we seem to have a solution at -2. And we also seem to have a solution at +1. So let's come up with this. So we have two solutions so far. X equals -2 and x equals +1. But now let's try to wrap everything that we know about this function. I know that the highest exponent is 5. So therefore, I must have 5 solutions. But if I take a look at my function here, I only have 2. So therefore, there must be 3 complex solutions. But let's hold on to that idea, because notice what's happening here at the solution x equals 1. Notice that in here, my graph, it touches the solution and it bounces out. So therefore, this solution must have a multiplicity that is even, either multiplicity 2 or multiplicity of 5. In x equals -2, notice that here we have an odd multiplicity. So either 1, 3, well, that's about it, because the highest that it can go is 5. So what we know so far is that we have 5 solutions, and we got the solution of 1 as being an even multiplicity, and the solution of -2 as being an odd multiplicity. So how do we properly define everything else that is needed to properly linearize our function? Well, since I know that -2 has an odd multiplicity, so therefore x plus 2 must be a factor. Well, since x equals -2 is a solution, well then x plus 2 is a factor. So let's factor it out. And how can we factor it out? Well, let's perform synthetic division. So let's go back to our original statement here. And let's just perform some synthetic division. So for that, remember that for synthetic division, first we want to see, well, is my polynomial written in standard form? So notice that it is not. So therefore, this is still equivalent to x to the 5th plus 0x to the 4th plus x to the 3rd plus 2x to the 2nd minus 12x plus 8. So now that is written in standard form, let's get the coefficients. The first coefficient is 1, then followed by a 0, then followed by a 1, then a 2, then a -12, and then an 8. And let's factor out x plus 2, so therefore my k is negative 2. And let's just perform this synthetic division. So what we got? We bring down the 1. So 1 times negative 2 is negative 2. We combine, that's negative 2. We multiply, that's 4. We combine, that's 5. We multiply, that's negative 10. We combine, that's negative 8. We multiply, that's negative 16. We combine, that's positive 16. We combine, that's 4. We multiply, that's negative 8. And we expect it to have a remainder of 0. So now what we know so far is that f of x can be seen as x plus 2 times what we got here as our conclusion from our synthetic division. The highest exponent was 5, so therefore this is the coefficient for x to the fourth. So we're going to get 1x to the fourth minus 2x to the third plus 5x to the second minus 8x plus 4. So notice that now we know that the first value that we got here should be a plus 2. So we got the first linear factor out. So now we want to factor it out, linear factorize it 4 times. So what we're going to be concentrating on is now this polynomial here. But we know that negative 2 had an odd multiplicity. So now let me concentrate on the solution of positive 1. And since I know that it has an even multiplicity, it's either 2 or 4. So now let's perform another synthetic division. Well, and let's just write it out. Well, since x equals 1 is a solution, well then x minus 1 is a factor. And remember that this one has an even multiplicity. So let's just do it. Now, let me perform synthetic division on this expression, not the original, but now this, because this is where I'm trying to make it smaller. So again, let me concentrate and see, well, are my exponents written in standard form? To the fourth, to the third, to the second, to the first, so everything's good. So let me just perform synthetic division. So now I'm going to get 1 minus 2, 5 minus 8, and a 4. Let's perform the synthetic division. And now I'm going to look at my factor as being x minus 1. So let me just factor it out. So therefore, my k should be of a value of 1. And now let's perform my multiplication. We bring down the 1. 1 times 1, that's 1. That's minus 1. We multiply, that's minus 1. We combine, that's 4. We multiply, that's 4. We combine, that's minus 4. We multiply, that's minus 4. We combine, so that's 0. So notice that we have a remainder of 0, which is what we expected, because we know that that was my solution. We know that x minus 1 is a factor. So now what we know so far is that f of x, we break it down. We already know that it's x plus 2. But now I know that this expression right here, it's equivalent of factoring out x minus 1. So let's factor it out. And now multiplying times the result that we got from our synthetic division. So my highest exponent was 4. So therefore, this 1 should be the coefficient of x to the third. So we're going to get x to the third minus x to the second plus 4 minus 4. So in other words, we're breaking down our f of x into linear form. So now I know that my second factor, it is of negative 1. Now notice that we need 3 more. So how are we going to get those 3 more? Well, we know that negative 1 has an even multiplicity. So perhaps I should factor it out one more time. So let's factor it out one more time. So let's just factor out one more time. So we're going to get 1. Now let's factor it out. And now what we're going to have here, the coefficient, or at least the values that we're going to place in our synthetic division are, the synthetic division is going to be performed on what is left of f of x, what is left of what we want to factor it out. So my first coefficient is going to be 1, then followed by negative 1, then followed by a 4, and followed by negative 4. So let's perform the synthetic division. So bring it down, that's 1. We multiply, that's 1. we combine that 0, and 0 times 1, it is 0. So we're going to bring this down. And 4 times 1, that is 4. And we got a 0, which is good. We got the remainder to be 0. So what we have shown is that now we got my first two linear factors. But now what we have shown is that this expression, x to the cube minus x squared plus 4 minus 4, that's equivalent of factoring out another x minus 1. And now what's remaining is just this, 1, 0, and 4. But these are the coefficients of the variables of x to the second, or 1 less than x there, which is x to the second. So 1 should be the coefficient for x to the second. Then we got 0x, and then we got plus 4. So now notice that now I know that my second factor, it's also negative 1. So all we're missing are just two more. We're missing two factors here. And we can get them from this expression. Now, we can perhaps try to guess them, but now, how about let's just make our life easier, because this problem is already long enough. So let's find just the solutions for this expression, x squared plus 4. If we find the solutions, we're going to get x equals negative 4. And if we take the square root, that's going to be x equals plus or minus the square root of negative 4, which this is just equivalent plus or minus 2i. So I have two solutions, x equals 2i and also x equals negative 2i. So therefore, we have properly found out the factors, where my factor is x minus 2i, and my second factor is x plus 2i. And that's essentially what we were missing here. Because now I know that the expression x squared plus 4 has the solution of 2i and negative 2i. So therefore, I can just break it down into its factors. And that's what we're missing. So now the next linear factorization is negative 2i. So let's just write it out. So negative 2i and positive 2i and positive 2i. Now, since this problem has already been a long process, let's just say that the coefficient that leads everything is just 1. And in that case, so it just disappears. All right. And now notice that we have properly linearized, or we have properly write down f of x as its linear factor. So here are the 5 linear factors: x plus 1, x minus 1, x minus 1, x minus 2i, and x, sorry, there should have been a plus 2i. And this goes hand in hand with what the linear factorization theorem says, because since we know that the highest exponent was 5, we should have been able to just rewrite it as a linear factor of 5 binomials, which we do have in here. So notice that this problem was a little bit complicated because we used a lot of things. The first thing that we used was the idea of the linear factorization theorem. We saw that the highest exponent was 5, so I knew that I was going to be able to break down into 5 linear factors. How do we get those factors? Well, first strategy, just graph it. Just graph the function and see how many real solutions you have there. In this case, we had 2, minus 2 and positive 1. And then look at their multiplicity. I saw that because it touches and it bounces back, then this solution has an even multiplicity. So therefore, it's either 2 or 4. It cannot be 6 because the highest is 5. So either 2 or 4. And I know that this should be 1. And then I just go one by one. Since I know that minus 2 is a solution, therefore x plus 2 is a factor. So let me use synthetic division to factor it out. And now I'm going to work with this. And then I look at the other solution. X minus 1 was a factor. So let me factor it out from this expression. And that's what we got here. I know that it had an even multiplicity, so let me factor it one more time. That's what we got here. And then we just solved the last one. And we saw that there were 2 complex numbers. And very important, notice that when it comes to complex numbers, the complex conjugate, it's a solution. If 2i is a solution, then negative 2i is a solution as well. So we got one more example that I would like to discuss with you, and that is, let's find a 4th degree polynomial who has real coefficients, and we know this about their solutions. We know that -1 is a solution, we know that -1 is a solution, and 3i is a solution. Well, notice that this polynomial is of the fourth degree. So therefore, we must have 4 solutions. But we already know 3. We know x minus 1 and x minus 1 are 2 solutions, but they're the same. But we can label as 2 solutions. And 3i is another solution. So we got 3 solutions here. We're missing 1. So how can we get the last solution? Well, remember that complex numbers always come in pair. So if 3i is a solution, then minus 3i is a solution as well, since it is its complex conjugate. So now I have 4 solutions in total. I have x equals -1, x equals -1, x equals 3i, and x equals -3i. So therefore, its factors for each of those solutions, if x equals -1 is a solution, then x plus 1 is a factor. Then x plus 1 is a factor. If 3i is a solution, then x minus 3i is a factor. And if -3i is a solution, then x plus 3i is a factor. So now notice that this goes hand in hand with what we started discussing here with our linear factorization theorem. It is of the fourth degree, so therefore, let's just write out our function with what we know. So now we know that f of x is equal to x plus 1 times x plus 1 times x minus 3i times x plus 3i. And I'm going to leave the multiplication for you to do it on your own. But notice that once we do our multiplication, you should obtain a polynomial who is of the fourth degree. And with this, it concludes our lesson for the fundamental theorem of algebra and linear factorization theorem using complex and real solutions.